Today, next speaker is Ming, as a distinguished university professor at Dr. Barry University, and the Dr. Barry University and Capital One innovative professor of political science at the University of Maryland, and I'm his as well. She is a fellow of the National Academy of Actors, ACM, IEEE, Graphics, and ACM, academics. Course as computational robotics, disability modeling, and simulation across more than 200 publications. In fact, she's received the IEEE EPROC 2026 Most Influential Paper Award. Congrats. And today she's speaking of data challenges with mobile learning. Let's welcome you.
Thank you, Peter, for the introduction. It is a great pleasure to be here. Back to Vienna again, of course, another ICRA. So today I'm going to talk about the data challenges in robot learning. We have been, living through some of the most exciting, at least for me, research years in the recent days. And I think part of it is the very fact that we are living through a data-driven revolution. The availability of the data comes in all different form, including 2D, 3D images, drawing, paintings, documents, videos, audios, medical records, all kind of web-based data, all kind of geometry and models and physics and dynamics, capture motion, simulated data, and all type of synthetic data, which I'm going to talk a bit about today. But also online, like social medias and, around the environment, like sensor data, for example, temperature, moisture, and all sorts of information that are being captured through traffic data, satellite images, and all kind of monitoring devices, including our iWatch. It's actually recording everything I've been doing, right? Our phone, it's listening all the time. So think about it. We live in an environment where data is being captured, everything we do. And so this means that we now have unprecedented level of data, but it's all kind of heterogeneity of information that is available and around us. It makes it possible to reconstruct, to synthesize, to predict, not just simulating the past events, but also the future evolutions. So I think we are living in an exciting time. And to me, personally, I not only work in robotics for decades, but I also work in virtual reality and simulation, particularly physics-based simulation. And I think for me personally, it is everything I do is to create what I think of the ultimate metaverse. It's a metaverse that transcends the boundary between the physical and the digital. It will bring both digital information into the real world and vice versa, taking the real world into this digital universe that we have created. And it makes it possible to achieve the impossible, such as predicting the system and the future that has not happened yet. And it gives us the virtual playground, which I'm totally enjoying today. And also a meta lab to test hypotheses, design new experiments and validating what we've been, thinking about and prototyping sort of new product and design. So I thought, at least personally, I think this is an exciting era that we live in, which is enabled not just by simulation, which I think many of us have been doing for a long time, robotics and automation, but also, empowered by the unprecedented level of data that we have. However, comes with the data are a diversity of challenges. It's not just the volume of data that we have to deal with, but also the generation process, the heating, the cooling, the electricity, the consumption of the energy, and so on, but also the biases and the noises and uncertainty that come with it, but also incompleteness. And I'm going to try to address some of these issues. To me, when we are talking about data, the assumption is we're just going to gobble up all the data that was already there on the web, on the YouTube. But we haven't really thought about every single images that we capture, it comes with a perspective biases. Every single video we recorded, it also come with the noises and uncertainty and incompleteness. And I like to also address the very fact that if we have garbage data, we're going to get garbage output. And then there's the issue of visibility, occlusions in the 3D environment. How do we address all of those issues? And most of all, most of the time when we capture these data, we are capturing them in an uncontrolled environment and process. Technically, we are also dealing with all type of generative AI and data-driven approach that offer more empirical model. And this is where I kind of come back and say, we really need to bring in the model that we already have. And I also like to acknowledge all the existing model we already have. Most of those model that we call physics-based, physics laws, they were also data-driven. The only difference is they were driven, they were derived by human in the loop, and often that they were also observed over centuries, more than decades. And so why throw away things that we already know? What's the difference between data-driven models that we have learned over hundreds and centuries versus the AI data-driven approach? And I think my personal belief is the two complement each other. At the end of the day, we have one law and one physical law that governs many things that we have and that we have seen. So we should be able to leverage one versus the other. And none of those are complete in the sense that a lot of them are all based on data that we have already observed or captured. And that's part of the reason that a lot of time these models don't necessarily also transfer across different tasks because it depending on the interactions. That's another aspect that I think the previous speaker already had touched upon. Interaction that captured due to collision, interaction that happen between human and the environment, interaction between objects. These interaction will arise to different parameters that we're talking about, like the frictional contact, like the parameter, the material parameters that we might have observed due to lighting, but also the contact forces, the compliances that we have to deal with when we perform manipulation. And these are the kind of things we don't think about and we don't talk about. And I'm hoping that, what I'm going to talk about today help addressing some of those problems. So in my view, parameters, physical parameter, material parameters, optical parameters, those are intrinsic to everything that we do. And often we don't have those numbers. And so this brings me back to one of the things I will be talking about, and that is the differentiable programming paradigm, specifically differentiable physics, where that we actually couple together data-driven approach along with model-based approach. And the other thing I would also like to focus on is learning purely from data can be extremely costly. I ask a very simple question. How much data is enough for us to teach robot to do what human does? Anyone have an answer or a bounds on that? Infinite, exponentially high, right? Because what we can achieve is infinitely vast. So it's experientially high for us to try to capture all those data. So what do? I think this comes back that we still need model. And that's kind of where simulation comes in. I believe that simulation can fill in the gap It's much cheaper to also generate simulation. And once you have the model, you can also refine your simulation model. And that is sort of the journey I have been on for the last few years, is trying to advocate a more cost-effective, a hybrid simulation combined with data-driven methodology to address some of these problems and challenges that we're dealing with. And I am one of the co-director for the UMD Gamma Research Labs. We have been dealing with both specialized robot automation as well as general purpose autonomy. Just to show you a little bit about what our labs have done. These are some of the mobile robot that was moving around, interacting with the environment, with human walking around. This, by the way, it's a perfect example of robot interacting with human on a regular basis also in dense crowds. Here we have another challenge. We have actually the robot dog walking around in grassy areas where it's not always visible. And again, this is some other representative challenges of a robot having to work with environment with uncertainty and unknown. We also have videos. I encourage you to check it out at Big Ten Network Spotlight, some of the work that in our group. But as I already mentioned and alluded to, one of the things I want to talk about here today is to learn the physical world with a differentiable simulator in geometry, where we really couple together an exciting new era of AI-driven algorithm designs, but also not giving away everything we already have known and that we have derived also from data with a human in the loop. And these are the existing physics model and geometric models. And in fact, that several of my PhD students have been working in this particular area. These are just sort of some of the simulation from prior work. And I want to say that some of those work that you just saw are very, very excitingly being incorporated into the product at Genesis AI. Just want to play really quickly what Genesis physics engine can offer. If you haven't seen this, you should check it out. And by the way, the company also exists. It has received hundreds of millions in seed fund. And their goal is to generate a simulation that can be used to train robots. You can see by having model, you can actually see what's going on and the physics that were being simulated. I'm just going to skip and go to various examples. It can handle all kind of many body problems, but it can also be used to train robots. And here is an example of manipulations of planes once you apply forces, deformable bodies. And it has a large language model interface. So I want to say that this is just a little pitch for Genesis. Check it out. If you have not, they have some really cool video and progress that just has been made. And I think this is a reality that we can expect.
Introducing our novel differentiable hybrid.
Here is another
Our simulator supports
hybrid
very large series
traffic simulation that we developed that is also differentiable,
microscopic methods. Note that
where we combine
is
both
differentiable,
the
including
macroscopic and microscopic simulation
to solve a variety of traffic problems. We can reduce congestion We can estimate parameters in the simulation. And we can train a pace car to control other vehicles.
And we can also integrate simulator with all kind of the most recent rendering and geometric representations, such as NeRF and Gaussian. And these are just sort of some of the examples where by combining these kind of approach together, we can also derive parameter directly from the video that we observed using the differentiable programming paradigm that I just mentioned. I'm not going into all the detail about the methodology, but I do encourage you all to check it out, some of our papers. And I also want to say this is actually one of the earlier work that we have done. And what I'm talking about here is not only applicable to interactions in the visual sense, but also in the auditory sense. All these audio material parameters were automatically extracted by real world recording, just a single world recording. So I'm going to quickly walk through 3 issues. One of them is efficiency and greener AI, and the other one is safety, which I think it's critical for all of us who work in robot learning. And last is how do you generalize? So the very first example about efficiency, I want to talk about some of the most recent work that we have done on time-aware world model. And so the basic idea here is that almost all the simulation that we have simulated, they actually have a time step that was part of it. If the time step is too big, then you could miss some of the important phenomena in between. If it's too small, it's very costly. What most of us, we tend to do is to simply use a very small time step to ensure stability. But it's beyond stability and it's beyond efficiency. This time step can also affect, if you have a world model, the sim to real gap. So if you train your model during the training time with a different time step, then what you actually use during inference, you have a gap in reality, in the simulated reality. And so this was basically what this paper was to address. I'm just going to tell you the quick underlying concept. What we ended up doing is to recognize different dynamical systems inherently are governed by the Nyquist criteria, depending on what the dynamics frequency will be. And so it's very difficult to preset what that delta T will be. And what we did is we did a multi-scale sampling strategy. We basically trained the system using a logarithm sampling strategy. So it is basically a multi-scale sampling during training. And so during the inferencing time, it doesn't matter what dynamical system you use, it's automatically adapt. So that's a basic idea. And this way, we can ensure that a Nyquist-Shannon sampling theorem is respected no matter what frequency that your system is running at. As I already mentioned, different dynamical system would actually run at different frequency. So this was a very adaptive, basically intelligent and also efficient way of building a world model using simulator. And that's the basic idea. I'm just going to skip through some of these details, and I welcome you to check out this paper. This was presented at ICML, I believe, last year. So on other things that what we have, and there's also theorem that go into detail regarding why this actually improve the efficiency. We have tested assembly, manipulation, task box closing, and I just want to show you the performance. On the very top, that is our models, and on the bottom, those are different baseline, but you could see ours achieve far higher rewards compared to the other. We have also applied this to various other baseline, and we have 2 different versions of our algorithm in red and in blue, and that those are time aware. But the only differences between the red and blue curves are the integration methods. And so this methodology also apply and work with different integration methodology. And the baselines are the dash line, and it's, you can see just right on the bottom. So ours consistently outperform the baseline, the best baseline that we can find. And these are just different experimental results that show the consistent of different robotic tasks that was being performed. And we also look at, as we change the sampling strategy during training, what would have happened? And with our approach, the baseline model degrade over time as you increase your influencing delta T. With our approach, it doesn't matter what it was trained at, and it also doesn't matter what the inferencing frequency will be. We are able to achieve excellent rewards, but also reconstruction of the events. We have also applied this concept of the type awareness to visual odometry. And I want to say that this paper, in fact, will be presented at CVPR right after ICRA this year. And it's basically taking advantage of the fact that the visual odometry should also be constructed with the temporal dynamics awareness of what's going on. Okay. So again, what we have seen is a consistent performance improvement with the time-aware approach. And I'm going to skip that and just go on and talk about other really important things, which we just presented at ICLEAR this year. And I think this is something I would love to advocate, is for us to really think about how do we bring temporal logic into our simulator to ensure robustness, but also most of all, safety. We have to bring logic into what we do to ensure that safeties are being guaranteed here. And the basic idea is most of the reinforcement learning algorithm, they just, satisfy some sort of reward function. We can incorporate linear temporal logic into reinforcement learning and specify the desired behaviors using LTL or linear temporal logic over the whole entire trajectory. And this will ensure no damage is being done. The robot doesn't damage any objects or hurt the human. Essentially, we are imposing additional cost constraints by introducing LTL. And what this does is just basically specify some of these safety logics in the, in the LTL formulation, and then it will work into the MDP automatically with this particular approach. What I want to mention is by incorporating LTL, what this does is introduce your problem in actually bring your problem to a higher dimensional space due to the sparse rewards. And what we actually did is we softened it by introducing a differentiable formulation that actually accelerate the computation by 1,000 times. And so this is a perfect example of ensuring safety while you also can achieve efficiency. Another aspect I want to mention, which is something that an area which I worked on for a few years on autonomous driving. And what some of my PhD students have been doing, this is including Wazy and David, and also Laura, who just finished and joined Waymo earlier last year. Basically, what we've been trying to do is to look at the corner cases. And we have shown in the earlier days through Wazy's work that we literally simulate accidents on purpose so that we can have this parameterized simulation for the autonomous driving simulator to learn how to avoid obstacles. And so that's the basic idea, is purposefully simulating all these accidental trajectory, and we can learn directly from the trajectory how to avoid some of these accidents. Laura has taken it one step further. We have looking into the U.S. National Highway Transportation Safety Agency's data, and we extracted 37 common category of accident, and we simulate all of them in the VR environment so that we have an immersive experience for the autonomous vehicle. We generated and created this data set called DISC, and I encourage those of you who are interested to take advantage of it.
Following these slides will be.
I'm going to skip the videos, but just encouraging you to check it out. One of the most recent work, which is currently under review, is through these data sets, we also, not just capturing a data set, we also did a personality test for every single driver who use our VR immersive simulator. So we also have the personality information, which we use to help us predict driving behaviors. So that the autonomous vehicle of the future can also taking into account the driver behaviors. If you know the driver around you, how they drive under different scenario, you will then be able to predict how they might drive in the future scenarios. And that's the basic idea. Lastly, I just want to say about the excitement about a foundation model. And so this is some of the work that I have done with one of my former PhD, Shan Yan, where we actually couple together simulation with optimization-based approach. And we can automatically infer the patient-specific parameters through videos or through simulator, and then we can take these simulator and create a virtual version of it for surgeon training. And so these are just material property that we extracted directly from the videos, and also medical data like the cardiac ultrasound. And this is the recover version of that. And this is a perfect example as what I just inferred to. Every single patient would have different tissue property. How do we get that information? If you can have a great simulator, but your parameters are wrong, you will not be able to use the right parameters to simulate the kind of patient-specific scenarios. But this is not just about the patient. It's also about the material. So we have extended this paradigm to recover the garment material. Clothes, it's how it drape on the body, really depending on the material. And this, in fact, this kind of technology was incorporated by Merch Amazon product for its first 3D virtual try-on. I'm also Amazon scholar, so this was one of the first 3D virtual try-on push out by Amazon. I will, again, I am not going to have time to talk about this work in too much detail, but I do encourage you to check it out. This was Junbang Liang's thesis. Going forward to the future, I think there are a lot of really exciting work to be said. The generalization from real to sim and sim to real. I want to say that for all the excitement that we have, one of the biggest problem in my view is how do we do sim to real? If our digital twin that we use to simulate does not truly reflect the reality, which means all kind of material properties and also object, human, data specific scenarios, then any simulation that we do and we simulate cannot properly reflect that reality to be transferred into the robot. And so I personally think in order for us to narrow that gap of sim to real, we must first do real to sim. And differentiable physics and differentiable programming paradigm was critical that coupled together the learning-based approach with the model-based approach where we can refine those parameters, but also optimize the result. But the other thing is adversarial training, which we also found to be very, very helpful for ensuring generalization and the robustness of a training for robotics foundation model. Okay, so I'm just going to end right here, and I realize I took up most of my time, but I probably can take one question really quick. Okay, we'll save the question. Thanks.